Does everybody know how to get to our YouTube channel? Okay, well, let me do this here. If my internet is working, it wasn't a while ago. Go to YouTube. Come on. I'm going to switch my account. Go to RF transmissions. And just to give you an idea of what we're doing for you is there are playlists. We have a block 6, we have a block 7, we got a block 2, and I've been doing block 4 videos. So if you come in tomorrow and you want to look at that particular, what we did tonight, bingo. Just come to this and hopefully I'll have it up and operational. I'll post it in the 2018 chat area when it's up and available. So that's what we're doing for you guys, and hopefully it'll help you in the long run and be able to refresh your memory on what we were able to cover. All right, so you say we have 2 more come in? Okay. Well, how about this? We just go ahead without them, and then they, make sure that when I post this, you let them know, hey, go to this. This is what we covered last night. So, first of all, we're going to clarify the modes of TDM. Now, when you say modes of TDM, were we talking, let me look here. That might be in another section. Can someone look real quick and tell me where that's at? Because I've got this pulled up to where we start into the signaling format section. Oh, it wasn't in the right one. Go figure that out. Okay. Slideshow. So I think this is in this is what happens. Nope, that's not in. It's going to figure I'm going to be in the wrong one here. Modes of TDM. Found it. Okay, so async and sync is what you're asking about, right? At least that's my understanding. Okay, so the 2 differences, and I mean, we can go through this and just go sign slot, time slots, frame bits only, wasted bandwidth. Okay, so let me try to give it to you in what I consider a little bit less convoluted than what you see on a slideshow. So think of it as a train pulling up to the train stop, and everybody's going to get on, but the only way you're going to get on is if the train pulls each of those cars toward you, and then there's so many people that can get on that box car. So what happens is with synchronous TDM is there's so much time that you're allotted to put X amount of people in this slot, and then it goes to the next one. So what happens is, and this goes over and over and over again, this is like a never-ending train, but it's got to get to the other end too. So what happens is if you've got all your box cars full, it's going to keep finding another place till another box car gets, but you are only designated, for example, if the train only has, let's say, 12 box cars, and you're supposed to get in boxcar number 4, but there's way too many people to get in boxcar 4, And that's the only boxcar you can get into. You can't get in boxcar 5, 6, 7, 8. So what happens is if no one's using those other boxcars, you still have to wait until boxcar number 4 comes by. So in other words, if you're not using it, you're losing that wasted time till the other boxcar gets in where they can fill it up and send it off. And it can be a major problem if all you're doing is waiting. But if you're not having to wait to get onto those boxcars, that's great. You can just keep going and going and going. But the problem you got is if you're only using 2 out of the 12 boxcars, that's wasted time. So that's what we're talking about when we have modes of TDM when we talk synchronous. So let's go on and you can see where the timing, everybody see the little boxes as you can see as A, B, C, D in frame 1. Well, you can see that the next frame, frame 2, C is missing. Why? Because there's nothing there. D can't use it. Alpha, Bravo, and Delta cannot use Charlie's frame. And then when frame 3 comes along, you can see where we have A, Alpha, and Delta. Well, they can't use Bravo and Charlie's frame, so that's wasted space. And then, of course, the last one, Alpha, is the only one that's got a lot of data to run. So the last 3 boxcars, they can't get filled up with A if there's more to it. So let's switch to async. Now, async is where you still have time slots. You're still assigned to boxcar 4. Wait a minute. Synchronous, asynchronous. There we go. When we go to async, this one is where you still have your boxcar to get into. But what's nice about this is they can redesign it to where you can go faster. For example, if everybody has to get on boxcar number 4, what the train sees was, well, gee, no one else is around. Let me hook up a whole bunch of 4s. And it's really flexible and being able to, cram everybody into, instead of waiting for the next train to come around for boxcar 4, they keep lining up boxcar 4 until all the data's empty. What makes this nice is if you got 12 boxcars, the train is sitting there going, well, gee, I only have number 4 boxcar that needs to be filled, so it lines up a whole bunch of 4 boxcars, and you're able to fill it up and send it down the line. Let's just say another crew comes in, and they got to get in boxcar, let's say 10. So 4 and 10's all it hooks up. But the problem you have with that is if you have all 12 boxcars that need to be filled, then it's going to take some time, and everybody has to wait until the next one comes through. Computers use this. There's a reason why sometimes you can't get on Boingo, especially during the midday to late afternoon. It's because everybody else is wanting to get on it. Kind of explain why you can't get on Boingo at certain times? Makes sense to me. See, just within my house, I have AT&T and I have 25 meg, and I can tell you right now, there are times where it gets maxed out, especially when I'm playing a game. Especially when I'm playing a game. He wasn't going to come in. I'll tell you later. Okay. So when I'm playing a game, and my son's playing a game, and my other son gets on and plays a game, well, we max out our things, and our ping rate goes through the roof because we're waiting on time. Oh, gee, yeah, game related on this. You didn't know that, did you? Everything is associated with what you do in the game and how much bandwidth you're taking up. So with async, it's flexible, but just remember it can be maxed out. Synchronous is it's a specific time at a specific rate. And again, you have to wait on your boxcar to come in. Async, you may get that boxcar quicker to come in. So those are the difference between async and sync. Did I answer your questions on that, or is there something else that you need to be explained, more explanation on? I'll wait till you guys chat in there. Are we good on that one? Okay, Larson said it's good. Drummer? Okay. Good. Moffett? Fantastic. All right, so let's go to the next one. And it says, for each signal format, explaining the voltage levels and why they are. So you guys want to see NRZ, CDI, and all those characters. Okay, you have come into the wonderful world of, oh boy. So you know that there's three. The big thing you want to take away from this is what is self-clocking and what isn't. It's more easier to say, well, which formats are self-clocking, because there's only three of them compared to all the rest of them that aren't. What makes them clock versus not clock? Well, internally in the multiplexer, and I'm going with what I know, is there's normally between 2 to 3 oscillators in there trying to sync up everything using phase-lock loop. Now guys, phase-lock loop's big in here. So you have the multiplexer. You have all the channels coming in, or users. Now I use that kind of interchangeably because the users can be one channel, one user, one channel, or one channel and multiple users. So you see how you got to twist and match these things up. So if you have one user, you can say, oh, we have 12 channels and 12 users. So those are interchangeable. But if you have, 6 users with 6 channels and the other 6 are multiple users on there, then it gets a little tough to look at what is really going on. So keep channels one thing. So everything's putting their input into, and I'm just using it from a transmit term, everybody is trying to get into the multiplexer. Well, an oscillator has to sync those signaling formats up so it can tell the internal part of the multiplexer what to do. So you may have several different formats coming into the multiplexer, and each one of those clocks are different, so you got to sync each one of those users up to get it internally to the multiplexer. Now the multiplexer is always known to use NRZ, non-return to zero, internally. That's how it syncs everything up, because it uses another oscillator to do that. And then when it gets ready to send it out, it uses another oscillator to send it down the road to the other multiplexer. So you can see that there's a lot of tugging and pulling and having to keep everything synced up. What they don't want you to do is get the signaling format so crazy that they've got to send clock pulses down, or an oscillator cycle sending it down to the dissonant. So sometimes we need to do it with a self-clocking format versus a non-self-clocking format. Most of the ones that I have seen out in the field that I have played with normally use CDI or NRZ. Now CDI is a self-clocking mode versus NRZ, which is not. So NRZ would have to have the oscillator send the signaling format in a clocked, in other words, 2 pieces, the NRZ signal itself as well as the clock. CDI doesn't need it. It just sends the signal down to the dissonant. The dissonant can sync it up. Hey, it knows what it's going on. Whereas NRZ, well, here's the signaling format. Here's the clock. Clock on the dissonant of the other multiplexer syncs everything up with it. So, with those 3 in mind, let's take a look at the first one, which is NRZ. There are two types, neutral and polar. So what makes those two different? Well, it's pretty easy. One has a 5-volt potential from 0 to 5. The other one has a 10-volt difference of potential. What does that mean? I can go over longer distances when you're looking at NRZ polar versus neutral. Neither one of them are self-clocking. They need a clock pulse to go to the distant end. So I'm going to back up one. You can see that we have at the top, this is our data. Okay, this is our data. What you don't see up at the top is the clock cycle. So there is, in just this cycle right here, there's one complete cycle showing us the 0 data. We have another cycle that happens with the 1 data. So those are 2 clock cycles that happen for 2 pieces of data, but you take a look at NRZ, how are you going to sync that up at the distant end? You're probably not going to be able to. The only way you're going to be able to is send that signal down to the multiplexer with its clock cycle. So when it gets to the distant end, the 2 oscillators talk to each other, syncs it up with phase lock loop, and voila, they're back in sync. You know, bye, bye, bye. You didn't get that? Bye, 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 in sync. Ooh. No, I did not see 20016. No one was in there. And when I looked on the schedule, no, it's all right. I didn't see him in the schedule anywhere. I saw 20018 after someone made mention, hey, we haven't had a stream. So it's all right. So as you can see, those two are not self-clocking. So we get the RZ. There are 4 types. You got neutral, polar, which are pretty much the same thing as NRZ, neutral and polar. Then you have RZ bipolar, and then bipolar zero suppression. So let's look at the first one, the neutral one. Again, it resembles the same thing as NRZ. It is not self-clocking. So when you take a look at this, oh, look at this. You have a resemblance of a clock cycle in this format, but there's no way to sync this up, so you need to send that separate clock signal with the format. But it's getting close, as you can see. This is what I'm talking about when we look at a clock cycle. Notice how it starts from right and goes left. You know why that is? Anybody? You can chat. It's a yes or no question. I'm willing to explain it. No. Okay. Let me see here. All right, you see the data at the top line? How do you read that? Let's see here. 1, 10, let's see. 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's 1,100,000, 100 million, 101 million and 110. Sergeant McCusker, help me out here. And he left. Figures. So you have 101 million and 110. If you take a look at that, you were thinking that I went from left to right. Well, that's not how you read numbers. You have to start here. Here's your ones. Here's your tens. Here's your hundreds. Start to see a picture here. Here's the thousands, tens of thousands, hundreds of thousands, millions, tens of millions, hundreds of millions. So we always use this mode in how we identify signaling formats and data. So if this was data and it was an 8-bit word, here's your 1, here's your 2, your 4, your 8, your 16, 32, 64, and 128. So from this point all the way from left to right is your 8-bit word, which we're getting ready to come up on when we look at PCM. So that's the reason why we write these data formats from right to left. And if you really take a look at a oscilloscope, you'll notice it always traces from right to left, and that's because of the way things operate. So let's take a look at polar. Now this one's a little different. You'll notice that we have a +5 and a -5. Again, we've got 10 volts difference of potential, but this one's self-clocking. Why? This resembles a clock. The difference is now we're looking at and adding data bits to it. But this is one complete cycle. This is one complete cycle. So there's a pattern here. And the distant end can see that pattern and say, hey, all I got to do is sync it up with my oscillator. I'm good to go. Now, the reason why they do that in both self-clocking and not self-clocking is because when you transmit data over line, you're going to get a degradation of the signal, and plus you have a lot of resistance. So what the timing might be at one end is going to be different when it finally arrives. So that's the reason why we have to see a clock cycle if it's self-clocking or not self-clocking. And with it like this, the distant end already knows how to sync it up, and we're good to go. So let's take a look at bipolar. Now bipolar is pretty much close to the polar, but there's a difference to it. With this one, it says I'm going to alternate between a +5 and a -5. What does that mean? It means that any time that I have a logic of 1, in other words, the data is saying, hey, I got a 1 here, it's going to either toggle to the +5 or it's going to toggle down to the -5, depending on how it is. So again, this is not self-clocking. And as you can see, well, we have this in one cycle. It looks pretty close. But you notice that, and I go back to the original state, anytime that we have a signal, we always start with a positive. That's a reference. We could have started with a negative. But most places I know of, we always start, when we are doing data, we always start with a positive. So this one is a positive. Here comes another 1. It goes negative. So you see the bipolar. It flip-flops. So the next one has to be a positive. The next one will have to be a negative. And that's how the bipolar works. Now the 10 volts, again, you can go farther distances with the 10 volts versus the 5 volts difference of potential. That's the only difference when we're looking at voltage levels. It's just a reference. So when we look at bipolar with 0 suppression, it's a little bit different. This one is self-clocking. Why? Because the distant end has been told, hey, with the zero suppression, meaning how many zeros in a row, if I got another 0, I'm going to throw what's called a bit violation. Well, what the heck is a bit violation? Well, what's the first part of bipolar? Well, it's got to flip between each set of those ones. But with a bit violation, the bit violation is going to emulate whatever the last one was. I'm talking the one data bit. So let's take a look at this. We have a 0 coming in, so nothing happens. We get a 1, so we always reference going positive to start with. We get another 1, data, and this one goes negative. We have 4 zeros in a row. We've told the distant end, hey, 4 zeros in a row, we're going to throw a bit violation on the 4th zero. This bit violation is going to emulate the last one here. So these two are telling the computer or the multiplexer at the distant end, hey, I got an issue here. You told me 4 zeros, I threw a bit violation. It knows to sync it back up. It knows at the distant end that it threw 4 zeros in a row, that, okay, that's my clock cycle. That's how it's able to tell it. Now, the NSM does this. The difference is it writes the way the NSM is writing that bipolar with zero suppression, it might be written in two different ways. I know that there was one where it said BP80ZS, and it's Bravo 8 Zulu Sierra. That's telling me there's going to be, if there's 8 zeros, the 9th zero is where it throws a bit violation. Then there's one, I think it says HD 4 Zulu Sierra, and that one says, hey, on the 4th one, I'm going to throw it. Now, it just depends on what that computer or the multiplexer wants done and how it's written as to how that bit violation is thrown. You don't really need to know that part. You just need to know that by looking at that, hey, this is bipolar zero suppression, or something called AMI, Alpha Mike India, which you'll see in the NSN. That's alternate mark inversion. It's the same thing as bipolar with zero suppression. There's also one in there where it says AMI, Alpha Mike India, alternate mark inversion, but there is no zero suppression. That one has to be clocked. So anything with bipolar with zero suppression is self-clocking. The last one, so far we got RZ polar, RZ bipolar with zero suppression. The third one for self-clocking is CDI. Now, what makes CDI so much different than the other signaling formats? One word: transitions. If you got a logic level 1, there's only going to be one transition. If you got a logic 0, there will be 2. Now, the reason for that is when it gets down to the distant end, because there's such, depending on how far it is, there could be a big lag, there could be a small lag. As long as these transitions happen in the clock cycle, you're good to go. So that's the reason why when you toggle it into CDI, the distant end is going to see that CDI, hey, this is self-clocking, so I'm either going to get a 1 or a 0 on this. I just got to look at the transitions. So if we look at this, realistically, you can see where 0 resembles a clock cycle and 1 doesn't. But it knows at the distant end, hey, this is a 1, this is a 0. Now, what they tell you, now down at the bottom here, it shows you a clock cycle. I wish they would have put it on all of them. This is the oscillator that's making this, and it's not being sent with it down the line. Just this signal is right here, where it's where you see the 2 transitions here, the 1 transition here. Now, what this does say is most of the time it will try to hit the leading edge, but it can happen anywhere in the clock cycle. So if this didn't happen on the leading edge and happened like let's say a split second afterwards, this second transition, as long as it happens in that clock cycle, you're good to go. The distant end knows it. So you don't have to send this with it. So that's the reason why we say the differences between clocking or self-clocking, or you need a clock cycle with it. So if this was not a self-clocking piece of information, you would have to send this clock with it down to the distant end. So there's two pieces of data that need to go down the wire to get to the distant end. All right, so does everybody kind of understand those voltage levels and the signaling formats and why they react like they do? You can chat. Okay, no other questions on this because we're going to hit PCM here. All right. So from what I understood on PCM, I saw that in one of your earlier messages. The first thing we look at is Nyquist theorem. Now, Nyquist theorem, believe it or not, all this can be researched except for CDI. I meant to mention that. CDI, the only way you can find that is it's called Manchester diphase. I don't know why, but CDI is something that the military uses, but you can't find it on the internet. I don't know if it's, copyrighted or protected or whatever. But Dr. Nyquist uses this Nyquist theorem. And what he said is when he was looking at this, it's the average voice is between 300 hertz and 3K hertz. So he rounded everything up and went to 4,000 hertz and said, you know what, it'd be great if I could sample this twice the highest frequency. Now this is solely for PCM for voice. We use it in the PRIC 150. Didn't know that, did you? So if you go back and you look at the PRIC 150 book, you'll see PCM in there when you're going from analog out of your microphone into, or your handset, into the digitizer, and it's PCM. Using the same concept that we're using here. So for PCM, Dr. Nyquist developed this. So the next one, we go through 3 different steps for it. Sampling, quantizing, and encoding. For sampling, what they told us, or what you should see, is each one of those samples are equal in that 1 second. So there's 8,000 times it happens per 1 second. Now I do want to tell you on that 8,000 times, 8,000 samples per second, is when you get into some really good programs, 8,000 times a second isn't very good. The more you sample, the better the quality. So nowadays, if you use, have you ever heard of the free software Audacity? Audacity can take a recorded voice or whatever and can sample it at ridiculous rates. I think the highest that I've seen it record at was 320K. Yeah, 320K. They also put insane on it too. They also have like the mid levels, which are in the hundreds of thousand, not 320K, but it's like 124, I think, and then he goes all the way down from the low end, which is 8,000 at the lowest end. But Audacity, you can look it up. You can use that free program if you want. So we look at PCM sampling. We're taking a sample of each one, and we have something called pulse amplitude. So we draw a line in the middle for this analog input here, and we convert it over, and you can see where each one of these has an amplitude to it. So all we're trying to do is take the digitized portion of that analog signal, and now we're going to put a number to it. So when we get to quantizing, the first one that we look at is this table right here. Now, if you could just picture one of those graph paper where everything's equal, left, right, up, down, this is what it's going to look at. But you'll notice that we have some that fall in between these numbers. So this is how everything gets quantized. We assign it a number. You see we have a plus 127 here and a negative 127 here. So I'm going to get to this in just a minute. So what is 127 times 2? If you can think through it real quick, you should get 254. Well, wait a minute. An 8-bit word is 255? Interesting. So, you see this table? This is like that graph paper. But we got a problem with it. Anytime that the pulse falls in between the number, we have something called a quantization error. Now, how do you describe a quantization error? It's kind of like distortion. But it happens so quick you can barely hear it anyway if you got good ears. Good luck with that. But it's happening so quick you probably won't notice unless you have a lot of these numbers falling in between the, like this one is between 3 and 4. Well, with 3 and the 4, what it looks at is just like with any rounding thing that you have, such as, 5 and above, that means you round up. 4 and below, you round down. That's what it's looking like. So it's using that. This is for the non-uniform. So we have that quantization error, and it's going to create some problems for us, especially if we got a lot of them. It's going to sound garbled if we do. How we prevent most of it, we don't prevent all of it, how we prevent most of it is we start moving the lines down further where the voice pattern is on a consistent basis. Most people. Now, you're always going to have that one person that has a very high voice, or that other person that has a deep vibrato, voice. So, yeah, they're going to be in that distortion area. But by squeezing these lines together, you still have 127 on the high end, 127 on the low end. Yeah, you got some issues here. So, when we take a look at this, we're able to eliminate most of the quantization errors. So now we got all the numbers assigned to the first two steps in quantization. Again, quantization error being that rounding, distortion. We got to encode it. So we have the plus 127, we have the minus 127. We still need to get to 255. How do we get to it? Well, the first 7 numbers equal to 127. 1, 2, 4, 8, 16, 32, 64. All those numbers add up to 127. Well, the last number, 128, when you add both of those to get 255, the 128 is used for either the positive or negative side of where that or when the quantization happens. So if you had a positive 127, that last eighth bit on the 128 should be a negative or a 0. If it's a negative 127, it's going to be a 1. Don't ask me why. Engineers did that. So, first 7 bits are all about where that quantization table is taking place, giving it a number, and that 8-bit tells us whether we're above the 0 line or below the 0 line. And that's how you quantize. So let's take a look at the actual encoding portion. You can see that, well, let's just take 2 here. We have 0, 1, which is 2, and everything else, but that 0 identifies that it is above the 0 line. If you have, let's just say, a 5, which is 1, 0, 1. That gives us 1, 2, 4. That's 5. But that last 8-bit tells us it's a 1, so it's going to be down below the 0 in the negative slot. So you see how all that pieces together. Now I'm going to carry on to the next two because it seems like we get some issues when we talk frame period. Frame period, if you take a look at this one sentence, the time it takes for one frame to occur, what that one frame is telling you is if you have a 24-channel multiplexer between, I'm trying to show you my fingers here, between here and here, that's one frame. All 24 channels are in here. In this case, we're using the 1 over 8,000 because that's what we're sampling at. We get 125 microseconds. But it's the time it takes one frame. Okay, so I've gone through all 24 channels. We've sampled it. This is how long it's going to take for 24 channels. When we get to the next one, the pulse modulated sample period, here's your 24 channels. I want to know how much time is in here for that one channel. In this case, we found out we have 24 channels. We divide it by the frame period, which was 125 microseconds, divided by 24, and we come up with 5.28 seconds. So if you take 5.28 seconds and take a look at each one of those 24 channels, it's going to add up your frame period. So frame period is big, PMSP is small. So PMSP is the times it takes to sample one in that one little frame. So those are the key between those two. And I hope I cleared that up because I get that a lot in some of the other classes too. All right, any questions on PCM and the frame period and pulse modulation sample period? Hello? Chat, please. Simple yes or no. Questions? All right. Larson. Okay, good. All right. So what's next? Carrier system concepts. All right. I'm a little confused about carrier system concepts, so can you write down there what you guys are wanting to know about it? You talking modem? Okay, good. Okay. Well, that would make sense. All right. How about if we go to FSK, ASK, and PSK? Yeah? No, maybe? All right. Let me pull up my other. Trying to remember where it is at. I think it's in 2 Bravo, but I'll take a look. That's the configuration. Let me get out of that one. Three Alpha, I think. That's basic radio picture. General modem principles, types of modulation. So that's where we need to be. All right. One thing that I get shocked with is a lot of you don't realize that a modem is taking a digital signal and converting it into an analog signal. Why? Well, digital signals aren't going to go very far. We've already proven that. And I think, what is it? Tesla and who was the other guy? Edison, I think. We're in a battle. I go watch it on the History Channel. But the easiest way to carry that digital code is by modulating it with an analog signal to get it down to dissonant, because AC goes farther. That's proven fact. So what we do is we use a different type of carriers in order to send it down to the dissonant. So first of all, we look at baud rate, or baud. And you can see it's the speed of the bandwidth, and it's also known as a symbol. Now, symbols and bauds, as you can see right now, it is interchangeable. So let's take a look at the different types of modulation. We got frequency, amplitude, and phase. Frequency. It's pretty easy to understand. We modulate the frequency with ones and zeros. So it is the first type. Teletype machines use it. You could actually say ham radio operators still use it today as what they call Morse code. It is 1 bit per symbol. And the big key thing here is you can see where the zeros are versus where the ones are. So here's our data of what just happened there. Here's the data of 1. You can see we have a higher frequency. We get the zeros. These are lower frequencies. So let's go on to the next one. ASK. Woo. This one, again, instead of the frequency, we do the amplitude. That's the difference between those two. Again, 1 bit per symbol. What does that mean, 1 bit per symbol? It's either got to be a 1 or it's either got to be a 0. That's what it means by 1 bit. So with amplitude, you can vary the amplitude with it. You can see we have zeros here. We have a lower amplitude. Kind of like the volume on your radio. You turn the volume up, your amplitude goes up. You turn the volume down, your amplitude goes down. Zeros, low amplitude. Ones, higher amplitude or larger. So the next one we look at is something called phase shift keying. 2 different types that we go through. One's BPSK, the other one's QPSK. Binary and quadrature. With binary, there's only 2 states. It's either a 1 or a 0. So with this one, when we look at phase shifting, we look at an analog signal, like an AC waveform. And what it's doing is when it intersects that 0 line, we're either going to change it or keep it the same for our 1 or 0. If it's a 1, it's not going to do anything. It's going to keep continuing. Once it goes to a 1 to a 0, then that's where that phase shift is going to happen. So halfway through that waveform is where it's going to shift. Whether it's from the top down or from the bottom up, it will shift it to either or. Now, I wish I had a diagram to show you on that, but just picture that AC waveform, and halfway through it is where it's going to shift. If it's, positive going and it needs to shift, it's probably going to keep another positive going and then go to the low. If it's a low, it's probably going to follow by another low and go on like that. Again, there's only 2 states with it. It's either a 1 or it's a 0. Here you go. See how it's going? So this is one complete waveform till it gets right here. It stays a 1. Now it's a 0. It's getting ready to go down, so it's going to emulate whatever it was doing prior and then go the opposite. So there's your phase shift. Now you got a 1 coming back in. Notice where it's phase shifting right here. We came down off of this low, came up to the 0 line. It's going to emulate what it was at the back end and keep that 1 going. And you can see for the other zeros and the 1s, Again, it's either a 1 or a 0. Do not confuse that name. Binary means it's either a 1 or a 0. Only one symbol. The next one is quadrature. What does it mean? It's going to shift that in 4 different places on that AC signal. Again, it's either going to be, in this case, you're either going to have a 0, 0, a 0, 1, or a 1, 0, or a 1, 1. So there's four different states, but it can only shift in 2. It's got 2 digits. That's the reason why it says 2 bits per signal, or 2 bits per symbol. Blech. So you have 4 different states, 2 digits to claim those 4 different states, and that's the reason why you see more than 2 bits. Now, we also look at quadrature, which is, I think the new TVs are doing this nowadays, which is the QAM. And also HF is starting to use QAM on the ham radio operators for sending data out. Now, what I wanted to get to was forward error correction, and I hope you guys know about forward error correction. It is a way to correct what happens on the distant end. Remember that quadrature sending 2 different, like a 0, 1 or 1, 0, and so forth and so on. This little 1/2 means that you're sending 2 of those bits down the line, but one of them is the original bit. The second one is a correction if it needs it. For a 3/4, it means that you've got 4 numbers. 3 of them, the first 3 are the data. The 4th one is the error bit. Now, the way it is put together on the distant end, if you go and look on YouTube, you'll find this thing called hamming. HAMMING code. Most of the time when you watch this, you hear the professor's name. You start to understand it in the first 2 or 3 minutes, and after that, they go off in the mathematical heavens somewhere. So normally you can see how it's all put together mathematically. So that's what this... I can't believe they called me. Anyway, that's what forward error correction means. The other part of this is it gets put together when you're looking at baud or symbol rate. What does that mean? Well, first of all, you need the forward error correction. You need the modulation bit, which is what we just went over. And then you have the data rate. Now there should be, good, here it is. As you can see, the data rate is important. We have the forward error correction, and we have modulation. And that's where that 1 bit per symbol comes into play. And when you have more, that's that quadrature or QAM. QAM can be anywhere between 3 to 10. So you can see why the modulation is important when we look at figuring out what their symbol rate or baud rate is. So there are 3 parts to this: data rate, forward error correction, and modulation type to get our symbol rate. We also have one last one, which I go over: interleaving, not interweaving, that kind of thing. Interleaving means you're mixing that data in with the forward error correction. So if you're sending a whole block of data, the idea is to keep only 1 or 2 bits from going south instead of the whole darn thing. Nothing is more frustrating than if you're sending, let's just say, a fax to someone and it's really important. It gets to the distant end and it's all skewed. They don't even know what you're getting. So this is the reason why you use that forward error correction, because you don't want to have to resend it. And believe me, I've had to resend a couple things and have to go to, I think it's UPS, to send off a document because they guarantee it. And I've sent it here from my home before several times, and sometimes it works, sometimes it doesn't. We get a noisy line every now and then, and that's what skews everything up. Is noise is the number one thing that happens on these lines to create the problems that you have on the distant end. So hopefully I cleared up a little bit for you. I mean, I could go on, but I know that you guys have dinner and that, so you guys want to call it for the night? Or do you want to continue on? It's up to you. It makes no difference to me. We can stream in the morning, too. And we can cover that other part, too. I'm okay with whatever. How about the other two? Moffat and Drummer. I'm with Larson. Moffat? What do you say? No pressure here. So no one's going to make a decision. That's good. Nice. Oh, you were... I'm not going to put that on there. But, yeah. How about this? What time in the morning do you think would be really good for you guys so everybody can be together and we can record it? Because I'll do it in the morning and I'll do it in the afternoon that way, because it seems like you guys got some more questions here on it. Especially the one with the signal flow. I mean, we could do this at 9 o'clock in the morning, 10 o'clock, and go to lunch, and then at 4 o'clock. It's up to you guys. 2 would probably be better, because then, you know, with this, I can, this is being recorded, so I can put this online. 1 a.m.? No kidding. So I take it you guys are nights from 12 o'clock until 8? I don't know what your nighttime thing is. 4 p.m. to 1. Oh, okay. All right. Well, that kind of makes sense. Well, then let's try 1 o'clock and 6 o'clock tomorrow. Would that work for you guys? Or no? 1 o'clock is definite. Okay, so 1 p.m. tomorrow, between 1 to 2 hours. Okay. Okay. So 1 o'clock, I think we could probably squeeze in just about everything else. And if you want, we can do a quick on Wednesday. When did you take your test on Wednesday? 4 p.m. Okay. So if you want, we can do tomorrow at 1 and Wednesday at 1, and I can go through and question and answer, period. Would that work out for you guys? Cool. So 1 o'clock tomorrow and Wednesday. Tomorrow will be whatever we don't cover. I'm going to post this on the YouTube RF transmissions as soon as I can. It'll be later on tonight, so that way they can catch up with everything. and we'll do the same thing on at 1 o'clock tomorrow. Record it, post it for you. And yes, I was going to send that in the chat. I was going to post it on our transmissions and put it in the chat for you. Good, good. All right then. Well, you guys have a pleasant night, and stay safe out there. Yes. It's going to be a long night for putting this on the YouTube channel, but it's worth it. All right. I'll talk to you guys later. Okay. And I got to stop it.